A brilliant star vanishes in a final, violent flash, but its story is far from over. These collapsed stars leave behind profound echoes that ripple through space and time, touching everything from the chemistry of our bodies to the stories we tell. By the end of this journey, you will understand how the death of a star is not an end, but a transformation that directly connects to your own existence. We will uncover how a star's explosive death can forge the very atoms of life, and why the ghostly glow of a nebula is a testament to cosmic rebirth. What does it mean that we are all living legacies of these ancient celestial events? Deep within the cold, dark clouds of gas and dust scattered across the galaxy, a story begins. These are the stellar nurseries, the quiet cradles where future stars are born. For eons, the gentle but relentless force of gravity tugs on tiny particles, pulling them closer and closer together. As this immense cloud collapses, it begins to spin and heat up, its core growing denser and hotter with every passing millennium. The pressure and temperature eventually become so extreme that they ignite the universe's most powerful engine, nuclear fusion. In this spectacular process, the star begins fusing hydrogen atoms into helium, releasing a torrent of energy that pushes outward, finally holding gravity's crushing inward pull at bay. This balance is the star's entire life, a sustained cosmic conflict that allows it to shine. A star like our Sun may burn steadily for 10 billion years, a seemingly eternal beacon. But this stability is an illusion, a temporary truce in a war that gravity is destined to win. The star's own mass is the key to its fate. A modest star like our Sun will eventually exhaust its nuclear fuel and shed its outer layers, leaving behind a dense, Earth-sized core called a white dwarf to cool slowly for eternity. But for stars many times more massive than the Sun, the end is far more dramatic. Their immense weight creates cores that burn through fuel at a ferocious rate, leading to a final, catastrophic collapse. It is this violent end for the most massive stars that forges the universe's heaviest elements and scatters them across the cosmos. So the serene life of a star, from its birth in a dark cloud to its final breath, is merely the prelude to its most important act, a transformation that writes the recipe for planets, for oceans, and for life itself. That final, catastrophic collapse happens in a single, breathtaking second. The star's iron core, no longer able to push back against the crushing force of gravity, gives way. It implodes at nearly a quarter the speed of light, and then rebounds in a titanic shockwave that rips the entire star apart from the inside out. This is a supernova. For a few glorious weeks, this single dying star can radiate more energy than our Sun will over its entire 10 billion-year lifetime, outshining every other star in its host galaxy combined. But this is far more than just a spectacular light show. In that unimaginable inferno of heat and pressure, a frantic, final act of creation occurs. Atomic nuclei are slammed together with such force that they forge every heavy element on the periodic table. The iron in your blood, the calcium in your bones, and the gold in a wedding ring were all born in the heart of a dying star billions of years ago. And for the very largest stars, the death is even more extreme. Their collapse results in a hypernova, an event so violent it focuses its energy into narrow jets that blast across the cosmos. These jets produce gamma-ray bursts, the most powerful explosions since the Big Bang itself, capable of emitting more energy in 10 seconds than our Sun will in its entire existence. These are not merely endings, they are the universe's primary forges, scattering newly minted elements like cosmic seeds into the void. The ghostly glow of a nebula we see through our telescopes is not just a tombstone, it is a nursery enriched by the ashes of its ancestors. So when you look up at the night sky, you are witnessing an ongoing story of destruction and rebirth, written in the very elements that make you, you. That brilliant flash of light from the supernova is just the opening act. The true, enduring monument to the star's death takes shape in the centuries that follow, as the expanding shockwave of debris, traveling at millions of miles per hour, plows into the cold, quiet gas of interstellar space. This collision heats the gas to incredible temperatures, causing it to glow with an ethereal, ghostly light. We call this a supernova remnant, a nebula that stands as a beautiful tombstone in the void. The Crab Nebula is one such monument, a vast and intricate web of shimmering filaments. Its vibrant hues are not random colors, they are the specific signatures of energized elements, the final breath of the star made visible. The reds are from hydrogen, the blues from oxygen, all swirling together in a cosmic dance that can persist for tens of thousands of years. Yet, within this celestial graveyard, something remarkable is already beginning. The very shockwave that carved this nebula also compresses the surrounding gas and dust, triggering gravitational collapse in new pockets of space. In the cold, dark regions of the nebula, new stars are beginning to ignite, often surrounded by the raw material for new planets. This means the nebula is not merely a cemetery, it is also a cradle. The death of one star directly enables the birth of its successors, seeding them with the heavy elements forged in the supernova's heart. To gaze upon a nebula is to look at a fossil record of a star's final moments, a beautiful and melancholic reminder that in the cosmos, every ending is woven directly into a new beginning. This profound cycle of death and rebirth prepares us to ask what remains after the nebula's glow eventually fades, leading us to the most mysterious relics of all. The nebula's beautiful glow is a temporary memorial. What remains long after its light has faded are the collapsed cores of those ancient giants, objects of almost unimaginable density. When the collapsing core of a massive star is left with a mass between 1.4 and 3 times that of our Sun, the force of its own gravity becomes absolutely unstoppable. It crushes the core so completely that protons and electrons are forced together, merging into neutrons. The entire star, once millions of miles across, is compressed into a perfect sphere no wider than a city. This is a neutron star. A single teaspoon of its material would weigh billions of tons on our planet, a mass equivalent to a mountain held in the palm of your hand. This is matter pushed to its ultimate limit. Some of these incredible objects reveal themselves through a cosmic illusion. As a neutron star forms, its magnetic field intensifies to trillions of times stronger than Earth's, and it can begin spinning hundreds of times every second. From the poles of this immense magnetic field, twin beams of radiation blast outward. If the star's rotation is misaligned, these beams sweep through space like the beacon of a lighthouse. From our distant vantage point, we see this as a rapid, perfectly timed pulse of energy blinking on and off with metronomic precision. We call these spinning neutron stars pulsars. Their discovery was a moment of profound revelation for astronomy. The first observed pulsar was so unnaturally regular that scientists briefly entertained the idea it might be an artificial signal, a message from an alien civilization. It was soon understood to be the heartbeat of a neutron star, the first direct proof that these theoretical objects were real. These spinning remnants are the universe's most accurate clocks, their steady pulses acting as persistent echoes of the violent collapse that created them. They are a stunning testament to the profound order that can emerge from cosmic chaos. Yet the extreme physics of these objects hints at a fate even more mysterious and absolute, a point where gravity wins its final victory. But even a neutron star represents a stalemate, a state where matter has been pushed to its absolute limit but still holds its ground. There exists a threshold, however, where gravity wins its final, absolute victory. When the collapsing core of a star contains more than roughly 3 times the mass of our Sun, no force in the universe can withstand the inward crush. The collapse does not stop at a city-sized ball of neutrons. It continues indefinitely, compressing all that immense mass into a single point of infinite density, a singularity. This is the birth of a black hole. The gravity around this point becomes so overpowering that it warps the very fabric of space and time, creating a region from which nothing, not even a single particle of light, can ever return. The boundary marking this point of no return is called the event horizon, a silent, invisible shroud that forever conceals the ultimate mystery at its center. We cannot see a black hole itself, for it emits no light. Instead, we witness its ghostly presence through its violent interactions with the universe. We see stars whipping around an empty patch of space at incredible speeds, orbiting an unseen, monstrous mass. We detect the final, desperate screams of light from superheated gas just before it crosses the event horizon. As matter is torn apart and spirals into the black hole in a structure called an accretion disk, it heats to millions of degrees, glowing fiercely in X-rays that our telescopes can capture. The formation of a black hole is the most final echo of a star's death, a gravitational tomb that permanently removes a massive object from the visible cosmos. Yet, in its profound silence, it continues to shape everything around it, its immense gravity dictating the motions of stars and the fate of entire galaxies. This relentless pull does not just affect matter. It warps the stage upon which the universe plays out, creating ripples in the fabric of reality itself. These ripples in spacetime are not just theoretical curiosities. They are real, physical waves that stretch and compress everything in their path as they travel across the cosmos at the speed of light. When two incredibly dense objects, like neutron stars or black holes, spiral inward and finally merge, they disrupt the fabric of reality in a way similar to a stone dropped into a pond. The resulting gravitational waves carry the unique signature of that violent event, a cosmic fingerprint encoded in the way the ripples oscillate and fade. For decades, this was a prediction waiting for proof. Then, in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first historic detection. The signal matched the final moments of 2 black holes, each about 30 times the mass of our Sun, colliding over 1 billion light-years away. The event released more power in gravitational waves than all the stars in the observable universe were emitting in light at that very moment. But we did not see a brilliant flash. Instead, we heard it. The signal was translated into a sound, a distinct chirp that marked the moment of merger. This was the universe speaking to us in a new language, one of pure gravity and motion. Every subsequent detection tells a story. The merger of 2 neutron stars in 2017, for instance, was not just heard, it was also seen. Telescopes around the world swiveled to observe the resulting kilonova explosion, an event that is now understood to be a primary cosmic forge for heavy elements like gold and platinum. This dual observation confirmed a profound connection. We can now listen to the vibrations of stellar death and then watch as that death creates the building blocks for new worlds. Our perception of the cosmos has fundamentally expanded, allowing us to witness the most dramatic transformations not just with our eyes but with our ears. That chirp from colliding neutron stars is more than a sound. It is the ring of a cosmic blacksmith's hammer. The extreme conditions of a supernova create a fleeting crucible where the universe forges its heaviest elements. During a star's stable life, its core fuses lighter elements like hydrogen into helium, and then helium into carbon and oxygen. But to build anything heavier than iron requires a cataclysm. In the heart of a supernova explosion, a frantic blizzard of neutrons bombards atomic nuclei. This process, called rapid neutron capture, forces nuclei to grow to immense sizes in a matter of seconds, creating elements like gold, platinum, and uranium almost instantly. Then, the supernova's blast wave hurls these newly minted treasures outward, seeding the surrounding cosmos. Every single atom of oxygen that fills your lungs was fused in the heart of a star that lived and died long before our sun was born. The iron that carries life, giving oxygen through your bloodstream, was forged in a stellar explosion. The calcium that strengthens your bones is the scattered ash of a cosmic giant's final breath. We are not just living in a universe built from stellar remains, we are those remains. Our bodies are a living archive, each of us a collection of atoms with a cosmic pedigree written in the fiery death of stars. This chemical connection is the most intimate echo of all, a direct physical link between the lives of long-vanished suns and our own. It means that when we look up at the night sky, we are not merely distant observers. We are the universe become conscious, looking back on itself, pondering the ancient, violent, and beautiful events that made our existence possible. That iron in your blood and calcium in your bones carries a story far deeper than biology. It is a narrative written in the language of nuclear fusion and stellar cataclysms, a truth that transforms our understanding of what it means to be human. The poetic phrase "we are stardust" is not merely a metaphor. It is a literal, scientific fact with staggering philosophical weight. It means the calcium that forms your skeleton was once part of the final, dying breath of a giant star. The oxygen you inhale with every breath was forged in a stellar core that ceased to exist billions of years ago. This knowledge bridges an immense gap, connecting the cold, hard physics of a supernova to the warm, beating heart of human experience. Suddenly, the death of a distant star is no longer a remote astronomical event. It is your own origin story. It is the reason you are here. This perspective invites a profound shift in how we see our place in the cosmos. The universe is not a cold, empty void we look out upon from a safe distance. It is our extended home. We are not just living within the universe, we are a conscious part of it, made from its very substance. Every person you meet, every living thing you see, is built from the same recycled star stuff, all of us sharing a common cosmic ancestry. This realization can evoke a powerful sense of awe, a humbling feeling that our individual lives are brief flickers in an unimaginably vast and ancient timeline. Yet it also brings a deep sense of belonging. You are not a stranger in a strange land. You are the universe itself, having become aware, looking back on its own history and wondering at its own beauty. This inherent connection to the cosmos carries with it a quiet responsibility. If we are all made from the same ancient stardust, then we are all fundamentally, materially connected to each other and to this fragile planet that has gathered and nurtured those elements. This sense of universal kinship may just hold the key to how we navigate our future here on Earth. This deep connection to the stars is not a modern revelation. For thousands of years, our ancestors looked up and witnessed these cosmic deaths firsthand. In the year 1054, a new star blazed into existence in the constellation Taurus, a point of light so brilliant it could be seen clearly in the daytime sky for 23 days. Chinese court astronomers, meticulous in their observations, documented this guest star, noting its color and its gradual fading over nearly 2 years. Half a world away, Arabic scholars also recorded the sudden, silent apparition. They had no telescopes, no understanding of nuclear fusion, yet they watched the violent death of a massive star over 6,000 light-years away. To them, this was not a scientific event. It was an omen, a message from the heavens that could foretell the fate of emperors or the rise and fall of dynasties. These sudden stars were woven into the fabric of human culture, interpreted as divine portents that shaped everything from religious belief to the decisions of kings. The very nebula we now study with our most advanced telescopes, the Crab Nebula, is the direct, visible remnant of that same star those ancient astronomers watched with awe and trepidation. Their detailed records have given modern science a gift, a precise timestamp that allows us to study the 600-year-old aftermath of that explosion with incredible accuracy. This long-standing fascination reveals a profound truth: the emotional impact of a star's death, the mix of wonder and fear, is a legacy that stretches back to the dawn of civilization. We may now understand the physics, but we still feel the same primal pull, the same need to find meaning in the brilliant, transient lights of the cosmos. Our ancient ancestors saw only a brilliant, silent omen in the sky, but we are privileged to listen to its enduring echo. Modern telescopes have become our time machines, capturing the faint light that has traveled for centuries and translating it into a detailed story of cosmic destruction and rebirth. We no longer see just a point of light. We see the intricate filaments of a supernova remnant, each a page from the star's final will and testament. The Chandra X-ray Observatory acts as our X-ray vision, peering into the incredibly hot, energetic hearts of these expanding clouds. It reveals the furious shock waves still traveling at millions of miles per hour, and the superheated gas that glows not in visible light, but in the high-energy X-rays that paint a picture of raw, ongoing power. Meanwhile, the James Webb Space Telescope uses its infrared eyes to see what our eyes cannot, piercing through the veils of cold dust that often obscure the heart of a nebula. It shows us the next generation of stars igniting within the funeral shroud of their predecessor, their infant planetary systems already coalescing from the enriched debris. Each wavelength of light, from radio waves to gamma rays, adds a unique color to our cosmic canvas. A single supernova remnant looks completely different when viewed through the lens of an optical telescope, an X-ray observatory, and an infrared instrument. Together, they reveal the full, magnificent scope of the event, from the blistering shock front to the cold, dark nurseries hidden within. This multi-spectral view transforms a distant flash into a rich, data-driven narrative, a biography of a star's death written across the entire electromagnetic spectrum. We are not just watching a silent movie from the past, we are assembling a symphony of light, where every instrument tells a different part of the same epic story. The silent light captured by our telescopes holds a hidden symphony. Since sound cannot travel through the vacuum of space, scientists have developed a remarkable way to listen to the cosmos, a process called sonification. They translate the raw data from objects like the Crab Nebula into sound, assigning different musical notes to brightness or creating sweeping tones based on the position of glowing filaments. The fierce X-ray light from a black hole's accretion disk might become a rising, piercing crescendo, while the gentle radio waves from a nebula's outer edges could translate into soft, ethereal chimes. What we hear is not a literal recording, but a data-driven composition, a new sensory layer applied to the ancient light. This sonic translation reveals structures and patterns that our eyes might miss, allowing us to perceive the dynamic chaos of a stellar explosion in an entirely new way. The result is often deeply moving, a complex and evolving symphony that feels both alien and strangely familiar. A supernova remnant does not sound like a single explosion, but like a vast orchestral piece with themes that emerge, clash, and fade over millennia. This auditory experience forges a different kind of bond with these distant events, transforming abstract numbers and false color images into something that resonates on a visceral, human level. It bridges the immense gap between cold data and warm feeling, allowing us to not just see the echo of a star's death, but to feel its vibrational pulse. This profound connection, built by turning light into music, shows how the legacy of these stars extends far beyond physics, inspiring us to weave their stories into the very fabric of our culture. That same awe we feel listening to a nebulous song has echoed through human culture for millennia. Long before we understood the nuclear physics of a supernova, we wove the drama of stellar death into our most enduring myths. The Norse spoke of Ragnarök, a final, cataclysmic battle where the world would be consumed by fire and flood, the stars themselves vanishing from the sky. This vision of an ultimate, destructive end mirrors the raw power of a hypernova, a cultural echo of a cosmic truth witnessed but not yet understood. Across the globe, cultures did not just see random points of light. They saw hunters, scorpions, and swans immortalized in the constellations, projecting their own stories of heroes, beasts, and journeys onto the celestial canvas. These patterns were a way to make sense of the vast, unknown heavens, to find familiar narratives in the silent, burning lights. This creative impulse did not end with the ancients. In the modern era, artists use digital brushes and paints to recreate the swirling, vibrant hues of the pillars of creation, translating telescope data into breathtaking visual spectacles that capture the public imagination. Science fiction authors craft entire sagas around civilizations watching their home star go supernova, using this ultimate deadline to explore profound human themes of mortality, legacy, and the desperate hope for rebirth among the stars. A dying sun in a story is never just an astronomical event. It is a mirror held up to our own fears of extinction and our deepest yearning to be remembered. When we paint a nebula or write about a star's death, we are not merely documenting the cosmos. We are processing the concept of endings and new beginnings on a scale we can barely comprehend, using art to give emotional shape to the cold equations of physics. This human need to find meaning in the stars is itself a form of legacy, a creative echo that runs parallel to our scientific quest. Both the artist and the astronomer are trying to read the same grand story, one through the lens of feeling, the other through the lens of data, each enriching our understanding of the other. This relentless drive to witness stellar death in real time has transformed astronomy into a global, high-speed race. Automated telescopes, like the Zwicky Transient Facility, now scan the entire visible sky each night, their electronic eyes comparing new images to old ones in a ceaseless search for change. The moment a new point of light appears where none was before, an alert flashes across the globe. It is a silent alarm for a cosmic crime scene that is already billions of years old. Within minutes, a coordinated response begins. Ground-based observatories swivel their massive mirrors toward the target. In space, the Swift satellite pivots to capture the high-energy gamma-ray and X-ray afterglow, while the Hubble and James Webb telescopes are urgently reprogrammed to interrupt their planned observations. This is not just about watching a light show. Each supernova is a unique natural laboratory, a fleeting chance to test the fundamental laws of physics under conditions we could never hope to recreate on Earth. The light curve, the way the explosion brightens and fades, acts as a cosmic barcode, revealing the exact type of supernova and the properties of the original star. The specific colors in its spectrum are the fingerprints of the elements being forged and scattered, allowing scientists to measure the yields of oxygen, silicon, and iron in near real time. This data is crucial for refining our models of how stars live and die, but the impact of these observations reaches far beyond stellar physics. Certain types of supernova, known as Type 1a, shine with a remarkably consistent peak brightness. This makes them perfect standard candles, celestial lighthouses of known intrinsic power. By measuring how much dimmer they appear from Earth, astronomers can calculate their distance with incredible precision. It was through studying these distant supernovae that scientists made one of the most shocking discoveries of the 20th century: the realization that the expansion of the universe is not slowing down due to gravity, but is instead accelerating, driven by a mysterious force we call dark energy. Every new supernova we find adds another date to point to this profound mystery, helping us measure the cosmos itself and perhaps one day understand the ultimate fate of all things. This scientific quest, this urgent need to catch the light before it fades, is a deeply human echo of the stellar processes we seek to understand. We are driven by the same fundamental forces that govern stars, a gravity-like pull toward knowledge and a radiant energy to explore. And this cosmic perspective inevitably turns our gaze much closer to home, to the star that gives us life and makes us wonder about its ultimate destiny. Our own sun will never experience that violent supernova death. Its fate is quieter, yet no less transformative. In roughly 5 billion years, this steady, yellow star will exhaust the hydrogen fuel in its core. The delicate balance between the outward push of fusion and the inward crush of gravity will break. For a time, the sun will burn helium in a desperate last stand, but this is only a temporary reprieve. As its core contracts and heats, the sun's outer layers will respond by expanding outward at a staggering rate, swelling to engulf the inner solar system. It will become a red giant, a bloated, ruddy orb that could swallow the orbits of Mercury and Venus whole. Earth will not be consumed, but it will be scorched. Our planet's oceans will boil away, its atmosphere will be stripped by the solar wind, and its surface will be baked into a molten, barren rock. The world that nurtured life for billions of years will become utterly uninhabitable, a ghost orbiting a dying star. This is not a story of explosive violence, but of a slow, inevitable transformation. The sun will eventually shrug off its entire outer atmosphere, casting it into space in a series of gentle pulses. This expelled shell of gas, illuminated by the intensely hot core left behind, will blossom into one of the sky's most beautiful objects, a planetary nebula. For tens of thousands of years, this glowing, intricate cloud will be a final, radiant monument to our star's long life. At its heart, the sun's core will remain as a white dwarf, an Earth-sized ember of degenerate matter, destined to cool slowly over trillions of years into a cold, black cinder. Contemplating this distant future makes the abstract cycle of stellar death feel deeply, unsettlingly personal. It connects the cosmic to the local, transforming a universal process into the specific fate of our own world. Our sun, the source of all light and life, will one day be the instrument of this planet's end. This knowledge carries a profound emotional weight, a sobering reminder of the impermanence that governs everything from stars to civilizations. It highlights the incredible, temporary preciousness of our existence on this fragile pale blue dot. We live during a brief, golden window in the sun's multi-billion-year life, a fleeting moment when conditions are just right for us to be here, to look up, and to understand our own place in this grand story. This perspective forces us to consider the legacy we wish to leave, not in 5 billion years, but in the centuries immediately ahead of us. If our own star has such a finite timeline, what does that mean for our responsibility to the life it currently sustains? And if this is the fate of a typical star, how many other worlds have witnessed or will witness their own suns setting for the final time? Our own sun's quiet fate is just one possibility in a galaxy teeming with diversity. As we discover thousands of planets orbiting other stars, their potential for life is inextricably linked to the violent or gentle death awaiting their sun. Imagine a young, watery world orbiting a brilliant blue giant star. Life there might just be beginning to stir in its oceans, but that world is living on borrowed time. Its massive host star will burn through its fuel in just a few tens of millions of years, a cosmic blink of an eye. Before any complex organisms could possibly evolve, the star will detonate as a supernova, bathing the entire planetary system in lethal radiation, utterly sterilizing every world in a flash. The window for life there was tragically short. Now contrast that with a planet circling a stable, long-lived star like our own sun, a class known as a red dwarf. That star may shine steadily for trillions of years, offering an almost unimaginably long, stable runway for life to arise, evolve, and perhaps even gaze up at its own night sky in wonder. The longevity and stability of a star is the ultimate cosmic clock, setting the schedule for life's grand experiment. This means the study of exoplanets forces us to see stellar death not as an isolated spectacle, but as a defining factor for biology on a galactic scale. The very same supernova that obliterates one promising solar system also performs a vital service for the galaxy. Its explosive shock waves trigger the formation of new star systems, and it seeds those nascent nebulae with the heavy elements essential for rocky planets and the chemistry of life. One star's death is a catastrophe for its immediate family, but a gift of possibility for its distant descendants. This creates a profound cosmic balancing act, where destruction and creation are two sides of the same coin. The emotional legacy of a star's death, therefore, expands far beyond our own human feelings. It suggests that any conscious beings anywhere in the universe must ultimately come to terms with this same reality. Their existence, their history, and their very atoms are tied to the life and death of stars. To be sentient is to understand that you live in a universe where your home star holds the power of life and death, a truth that connects all potential civilizations across the vast, star-scattered darkness. This emotional pull we feel toward dying stars is not a coincidence. It is a reflection of our own deepest human experiences, mirrored on a cosmic scale. We all understand the pain of loss, the quiet ache of watching something brilliant fade from our lives. When we see a star's light extinguished in a final, glorious flash, or the serene, ghostly beauty of its expanding nebula, we are witnessing a metaphor for our own mortality. It is a grave marker written in light and gas, a testament to an ending. Yet within that image is also a promise of transformation. The nebula is not just a tomb, it is a cradle. The star's death directly enables new possibilities, scattering the essential ingredients for future stars, planets, and perhaps even new life. This cosmic perspective does not diminish our personal grief, but it can frame it within a vast, beautiful, and impersonal cycle. Our own endings, our own losses, become part of a grand, universal pattern where death is not a final stop, but a necessary step in an ongoing story of rebirth. The profound realization that the atoms of our bodies were forged in these ancient stellar furnaces transforms this from a mere metaphor into a physical truth. Your grief for a lost loved one is not separate from the cosmos. The calcium in their bones and the iron in their blood was once stardust and has now returned to the universe in a different form. This knowledge can be a strange and powerful comfort, a feeling that we are all eternally connected to a magnificent, ongoing process far greater than ourselves. This is why the death of a star moves scientists and poets in equal measure. One seeks to understand its physics, the other to give voice to its emotional echo. Both are trying to comprehend the same beautiful, heartbreaking truth about endings and the legacies they leave behind. This shared human response invites us to become more than just observers, to find our own way to engage with this eternal cosmic story. You do not need a billion-dollar telescope to become part of this cosmic story. The relentless digital gaze of automated sky surveys produces more images of distant galaxies than any single team of scientists could ever hope to analyze. This flood of data has created a beautiful opportunity, a call for help that anyone with an internet connection can answer. Online platforms like Zooniverse host a universe of citizen science projects where you can look at real, raw data from the world's most powerful observatories. You might be the first human being to ever lay eyes on a distant galaxy in the process of colliding with another, its spiral arms stretched into long, ethereal streams of stars. Or you could be the one to spot the tiny, new pinprick of light that signals a supernova exploding in a galaxy millions of light years away. This is not a simulation. You are looking at the genuine article contributing directly to the front lines of astronomical discovery. Each classification you make, each potential supernova you flag, becomes a vital data point in a much larger research paper, helping scientists understand the patterns and frequencies of these cosmic deaths. This process democratizes discovery, transforming the search for stellar echoes from an elite pursuit into a shared human endeavor. When you participate, you are no longer just learning about the death of a star, you are actively helping to document its legacy. That personal connection transforms your relationship with the cosmos. You are not just being told that a star died, you helped find the evidence. You become part of the chain of discovery, touching the same data that will one day be used to map the history of our universe. This active participation makes the emotional weight of stellar death feel more immediate and more profound. It is one thing to hear that we are stardust. It is another to spend an hour sifting through the birthplaces of that stardust, knowing your curiosity is directly adding to the sum of human knowledge. This flood of cosmic data is more than we could ever process by hand. Modern observatories and gravitational wave detectors generate a staggering volume of information, a digital ocean of light curves, spectra, and spacetime ripples measured in petabytes. To navigate this deluge, scientists are turning to sophisticated algorithms and machine learning. These are not just simple search tools. They are digital detectives trained to find subtle patterns in the noise, to spot the faint, unique signature of a distant supernova remnant, or predict the complex behavior of a swirling accretion disk around a newborn black hole. This computational power allows for something truly remarkable. Researchers can now create incredibly detailed simulations of a supernova explosion, modeling the intricate dance of shockwaves and nuclear reactions from the first millisecond of collapse to the expansion of the nebula centuries later. These virtual stellar deaths are then compared directly to the real data we collect from telescopes. When the simulation matches the observation, it confirms our theories. When it does not, it points toward new, undiscovered physics, forcing us to revise our understanding of how stars die. The light and gravitational waves we capture are a form of cosmic fossil record. By mining this data, we are not just studying a recent explosion. We are performing a kind of celestial archaeology, using the echoes from a nebula to reconstruct the mass, composition, and life story of a star that perished millions, even billions of years ago. Each piece of data is a clue, and together they allow us to exhume the histories of these ancient giants, pushing our knowledge toward the next great mystery. Even with all we have learned, the final moments of a massive star's life are still shrouded in mystery. Our most powerful computer simulations cannot yet fully replicate the chaotic physics of a core collapse supernova. We know the star's iron core implodes, but the exact mechanism that reverses this collapse into a titanic explosion, the shock wave that tears the star apart, remains one of the greatest unsolved problems in astrophysics. Does a sudden flood of neutrinos push the stellar material outward, or do violent vibrations within the newborn neutron star provide the final, decisive kick? The truth is, we are still not entirely sure what flips the switch on this cosmic bomb, and the mysteries only deepen when we consider the bizarre remnants left behind. Within a neutron star, matter is crushed into a state that does not exist anywhere else in the universe. Is it a perfect, frictionless superfluid, or a solid crust of exotic nuclei floating on a sea of neutrons? We simply do not know the true nature of this matter pushed beyond any earthly limits. These stars are cosmic laboratories for physics we cannot hope to recreate, and their secrets are locked away behind immense gravity and distance. The riddles extend far beyond the explosion itself, out into the expanding debris cloud. Supernova remnants are believed to be natural particle accelerators, their turbulent shock waves acting as cosmic cannons that fire subatomic particles across the galaxy. Some of the most energetic cosmic rays ever detected, particles carrying the energy of a professionally thrown fastball but compressed into a single microscopic speck, are thought to originate here. Yet, we have not been able to definitively trace these ghostly bullets back to their source, to catch the remnant in the very act of acceleration. This is more than a simple gap in our knowledge. It is a fundamental question about the invisible, high-energy forces that constantly bombard our planet. Perhaps the most exciting clues come from the supernova that break all the rules. Astronomers have now observed explosions that are inexplicably bright, shining with the power of dozens of normal supernovae, while others are surprisingly faint and short-lived. These outliers do not fit our neatly defined categories. They hint at exotic stellar deaths we have not yet imagined, perhaps involving supermassive stars that collapse directly into black holes, or the tumultuous merger of two white dwarfs. Each of these cosmic anomalies is a crack in our current understanding, and through that crack we can glimpse the possibility of entirely new physics. Every unanswered question is a frontier, a destination for the next generation of explorers. The enduring allure of stellar death lies not only in what we have discovered, but in the profound mysteries that remain, waiting for the tools of the future to illuminate them. These lingering mysteries will not remain unanswered for long. A new generation of cosmic observatories is being built, designed specifically to interrogate the final moments of stars with a clarity we have never before possessed. The upcoming Nancy Grace Roman Space Telescope and the ground-based Vera C. Rubin Observatory will act as tireless digital sentinels, scanning vast swaths of the sky night after night. They are not built to study a single star in detail, but to capture the big picture, discovering not dozens, but thousands of new supernovae every year. Each of these dying stars is a data point, a single brushstroke in a grand portrait of cosmic expansion. By mapping the brightness and distribution of so many stellar explosions across billions of years of cosmic history, these telescopes will measure the universe's accelerating expansion with a precision that could finally reveal the true nature of the dark energy driving it. We are moving from studying individual deaths to understanding the demographics of stellar mortality on a cosmic scale. and our ears, too, are getting an upgrade. While LIGO listens to the high-pitched chirps of stellar mass black holes, the future space-based LIS mission will open an entirely new auditory range. Its giant, laser-linked triangles will float in space, sensitive to the low-frequency rumbles that shake the fabric of spacetime. LIS will hear the deep, resonant gong of supermassive black holes merging at the hearts of galaxies, events that have been utterly silent to our current detectors. It will allow us to listen to the universe's bass notes, the gravitational waves from collisions so immense they can last for months, building to a crescendo that has been ringing through space since the first stars died. But we will not just be listening from a distance. Advanced instruments on a new class of giant ground-based telescopes will give us something akin to a front-row seat. They will use sophisticated adaptive optics to cancel out the blurring of our atmosphere, producing images of such sharpness that we can directly watch the violent whirlpools of accretion disks and the searing jets of plasma screaming away from newborn neutron stars and black holes. We will no longer be reconstructing these events from indirect clues. We will be witnessing the chaotic aftermath of stellar collapse as it unfolds in near real time. These missions are more than just tools. They are the next chapter in a very old story, a story that began when a human first looked up at a strange new star and wondered what it meant. The data they return will undoubtedly contain surprises, phenomena we have not yet dreamed of, forcing us to rewrite our models and rediscover the universe all over again. The emotional legacy of a star's death is not a closed book. It is a living narrative, and we are just turning the page. This breathtaking beauty is a cosmic paradox. We are drawn to the delicate, lace-like filaments of the Veil Nebula and the haunting, symmetrical gaze of the Cat's Eye Nebula, yet these are the scars of unimaginable violence. Their vibrant palettes are not an artist's choice, they are a chemical language written in light. The deep reds are the signature of energized hydrogen, the star's most abundant fuel. The brilliant blues come from oxygen, atoms forged in the star's core during its stable life. The subtle greens are often the glow of sulfur, an element created in the stellar furnace's final, desperate moments. Every color is a direct, visual readout of the elements being scattered into the void, a dying star's final composition made visible. We are witnessing the ultimate recycling program, where the raw materials for future planets and life are painted across the canvas of space. This forces us to reconsider a fundamental idea. We often see destruction and creation as opposites, the end of one thing and the beginning of another. But in the cosmos, they are the same event. The force that tears a star apart is the very same force that assembles the periodic table and seeds the galaxy with potential. A supernova is not a funeral, it is a dispersal of life-giving ingredients on a galactic scale. The photographs from the Hubble and James Webb telescopes capture this duality, transforming data into art that resonates on a deeply human level. We do not need to understand nuclear physics to feel the awe inspired by the pillars of creation, to sense the immense power and delicate beauty held in that single frame. This visual gateway makes the science accessible, pulling us into the story through our innate response to splendor. Yet within that splendor lies a silent warning. The same processes that painted these gorgeous nebulae will one day spell the end of our own world when the sun dies. The beauty is real, but it is the beauty of a phoenix, forever tied to the flames that consume it. This cosmic beauty holds a hidden danger. While we often watch these stellar deaths from a safe distance, a supernova occurring too close to our solar system would be a very different story. If a massive star within about 50 light-years of Earth were to explode, its consequences would be direct and devastating. The initial flash of gamma rays, followed by a torrent of high-energy cosmic rays, would strike our planet's atmosphere like a cosmic tsunami. This invisible assault would not scorch the ground, but it would chemically dismantle the fragile shield that protects all life on Earth, our ozone layer. With that protective blanket torn away, the planet's surface would be bathed in lethal levels of ultraviolet radiation from our own sun. The result would be a planetary-scale catastrophe, collapsing food chains from the bottom up by killing off phytoplankton in the oceans and triggering a mass extinction that would reshape the history of life. This is not mere speculation. Geologists have found potential evidence in our planet's deep past, thin layers of rock containing isotopes like iron-60, a radioactive element that is forged only in supernova explosions. These cosmic fingerprints suggest that Earth may have been sprayed with the debris of a nearby stellar death millions of years ago, an event that could have coincided with periods of significant biological turnover. This sobering possibility forces us to look at the galaxy with new eyes. The same brilliant beacon that signals the creation of new elements also carries the potential for annihilation. This duality adds a layer of profound urgency to modern astronomy. Identifying and monitoring the massive, unstable stars in our immediate galactic neighborhood is no longer just an academic exercise. It is a form of cosmic vigilance, a necessary step in understanding the potential threats that lurk in the darkness between the stars. The emotional legacy of stellar death thus expands to include a quiet hum of vulnerability. We are not just the beneficiaries of ancient stellar explosions, we are also potential victims of future ones. This awareness, however unsettling, also deepens our gratitude for the remarkable, temporary stability we currently enjoy, a fragile peace granted to us by the vast, insulating emptiness of space. This profound connection is not just a story told by light, it is a truth we can hold in our hands, deep within the most primitive meteorites, the ones that have remained largely unchanged since the dawn of our solar system. Scientists have discovered something extraordinary. Hidden in the dark, rocky matrix are microscopic specks of dust far older than the Sun itself. These are presolar grains, tiny mineral fragments that did not form in our own solar nebula. Each one is a literal piece of stardust, a solid shard that condensed in the cooling atmosphere of a different, long-dead star. Before our Sun even ignited, this dust was drifting through interstellar space, and by a miraculous chance, it was swept up into the raw material that would become our planetary system. These grains are more than just ancient, they are individual time capsules, each carrying the unique chemical signature of its parent star. To find one is to recover a fossil from a stellar giant that perished billions of years ago. The process of studying them is a feat of modern alchemy. Researchers carefully dissolve the meteorite rock away with acid, a process that leaves behind only the toughest, most resilient minerals, the stardust itself. Then, using instruments called ion microprobes, they blast individual grains with a beam of charged atoms. This technique allows them to measure the grain's isotopic composition, which acts as a precise stellar fingerprint. Every star has its own unique blend of elemental variants, forged in its specific nuclear furnace. A grain rich in certain types of silicon and oxygen might have come from the gentle outflow of an aging red giant. Another, laden with specific isotopes of calcium and titanium, could only have been forged in the violent heart of a supernova. This means we can now sort these microscopic treasures by their celestial origin, placing a tiny piece of a specific type of stellar death on a slide for study. So when you hold a meteorite that contains these grains, you are not just holding a rock from space. You are holding a physical collection of artifacts from other suns, a museum of ancient stars preserved within a stone. This tangible evidence transforms a beautiful idea into an undeniable physical fact. The iron in your blood and the oxygen in your lungs is not an abstract concept. It is the same substance as these grains of stardust you could, in principle, hold in your palm. This brings the entire cosmic story full circle, connecting the grandest explosions in the universe to the smallest, most durable particles, a legacy written not just in light but in stone. Our journey through the echoes of collapsed stars reveals a universe where death is not an end but a transformation. The violent beauty of a supernova, the silent, metronomic ticking of a pulsar, and the invisible, profound pull of a black hole are not separate events. They are all part of a single, grand story of cosmic recycling, a story written into the very fabric of our existence. We have traced this emotional legacy from the forge of stellar explosions that created the iron in our blood, to the ancient human impulse to see omens in a new star, to the modern scientific quest that uses these deaths to measure the accelerating universe itself. Every layer of this story connects the vast and impersonal cosmos to the deeply personal. It tells us that we are not just living in the universe, we are a product of its most dramatic and creative moments. You are a living testament to this grand cycle, a collection of atoms with a cosmic pedigree. The calcium in your bones, the oxygen in your lungs, these are the scattered ashes of stars that shone brightly billions of years before our sun was born. This knowledge is more than a scientific fact. It is an invitation to feel a profound sense of wonder and connection. It offers a perspective where our own lives, with all their joys and endings, are part of a magnificent, ongoing process of destruction and rebirth that spans the entire cosmos. This perspective also carries a quiet responsibility. If we are all made from the same ancient stardust, then we are all fundamentally connected to each other and to this fragile planet that has gathered and nurtured those elements. Let this understanding inspire not only awe as you gaze at the night sky, but also a deeper care for the world and the life that shares this extraordinary cosmic heritage with you. We would love to hear what part of this story resonated most with you. Share your thoughts on this cosmic legacy in the comments below, and if you want to continue exploring the mysteries of the universe, subscribe to join us on the next journey.